Hello. So in this short slash long video, we are going to look at solving systems of equations by using the graphing method. And specifically, those systems that we're going to be looking at are going to be of linear equations. So let's just talk about a quick definition. What is a system of linear equations? Well, it's two or more linear equations for which we want to find the one solution, if it exists, that would make all the equations in the system satisfied. And I'll explain what that means here in just a second. So, number one, no, a system can have more than two equations, but we're going to focus mostly on systems with two equations. And no, that systems in general don't have to include linear. Okay, so the fact that we're saying systems of linear equations is significant. That means all of the shapes that we'll see when we graph stuff will be straight lines. Okay. So here's an equation, right? And here's an equation. So if we wanted to know a point, so an x and a y, that would make this equation on the left-hand side here, this first equation, true, we could plug in a given x and calculate a potential y, right? And if we did that repeatedly, we would graph it. Same with this one down here. If we picked, let's say, the x value of 3, if we were to plug in 3 right here, and we were to do the calculations, 3 times a third is 1, and 1 minus 3 is -2. Our y would be -2. And we would know then that this point right here, 3 and -2, is on this line. So the question becomes, what would present itself as a solution for both of these equations at the same time? So does an x value and a y value exist that would present itself as a solution to this equation and to this equation? So is there one x and one y that would work for both? And that, my friends, would be considered the answer, I guess, to this system. It is possible for systems to have no solution. It is also possible for systems to have infinite solutions. We'll talk about that in a second. But right now, let's talk about one solution systems like the one in this example. All right, on the next slide here, I'm going to show you what these look like graphed. Quick sloppy handheld video. Here are those equations plugged into Desmos. So you can see the top one there, the red, and then the blue one. And that point right there where my mouse is moving, that right there is the one point where these two lines intersect, point 3, -2. That would mean then, because they intersect there, that if we were to plug in 3 into the x's and -2 into the y's on both of these equations, that it would work. Because remember, every point on the blue line is a solution for this equation right here. And every point on the red line is a solution for this equation right here. So if we have a point that's both on the red and the blue, then it can't help but be a solution for both of them. Pretty cool. So I wanted to just show you real quick how we would check our solution. So when I plugged these into Desmos, it looked like they intersected at the point 3, -2. In fact, that's what Desmos told me. I'm going to ask you guys not to use Desmos and to actually graph these by hand, but at the end you could definitely use the Desmos graphing calculator or some other graphing calculator to check them, but I don't want you to be misled. Just the fact that I use it doesn't mean I want you to use it. You need to know how to graph these by hand because that's the way your test is going to do it. So this theoretically then, if this works, means we could plug this in for our x and this in for our y's and it should work. So let's try that. So we have our y of -2 should be equal to -5/3 times 3 plus 3. And then in this equation, which was the second one, we should have -2 being equal to 1/3 times 3 minus 3. So let's see if this point works. Well, let me start on the left-hand side. And I'm just going to simplify the right-hand side, and if it equals -2 when we get a true statement, then we know that the point 3, 2 worked for it. So -2 equals, now I got to do some math. What's 3 times -5/3? Well, that'd be -15/3 plus 3, which is going to end up being -5 plus 3, which results in this final statement. -2 does equal -2. Therefore, this point made this equation true, so it must work for that equation. Let's check the other one. -2 equals 1/3 times 3 minus 3. Oh, I didn't even do anything on that step, my mistake. Negative 2 equals 1 minus 3 because a third times 3 is 1. And so we get the statement negative 2 equals negative 2. So, my goodness, this also works for this equation. So it is a solution. It is the spot in two-dimensional space that's going to satisfy both equations. And we found it by looking at where the two lines intersected. So now I'm going to show you 3 examples. I'm going to show you an example of a problem with one solution, much like this one. I'm going to show you an example of a problem with no solutions and an example with infinite solutions. But if you want to pause the video for a moment, this would be a good idea, and see if you can't think of a system or a situation where no solution for two lines would exist. In other words, no intersection of the two lines. And then hit play on the video and see if you are right. All right, let's take a look at these examples. Okay, so pretend the directions say, I didn't quite have room to write the directions. Solve this system of linear equations through the graphing method or something like that. So the first thing you want to do, if you like to write down steps, the first thing you want to do is make sure both of your equations are in slope-intercept form so they're easy to graph. This one is right here, so we're good. This one right here is not. The one on the top is not in slope-intercept form, so it's going to be difficult to graph it. So let's do some rearranging to the equation to do that. The second step would be to graph them. And the third step would be to make an observation and determine a solution. So I'm going to start out by adding y to both sides of this equation because I want to get y on the left here. So we got y equal minus 4x equals 3 now, right? And then I'm just going to add 4x to both sides. So y equals 4x plus 3. That's how I rearrange the equation. Now both of our equations are ready to go so I can graph them. So y equals 4x plus 3. 3 is my y-intercept. And then I know 4 is rise over run. So I've got a rise of 4 and a run of 1. So if I go up 4 and over 1, I'll kind of get my line. And I can do that in reverse. I can drop down 4 and go left 1 just to get a good idea of the line. And so I can kind of see my line now. I've got 3 points, so I'm going to attempt a sloppy graph. I still haven't conquered the neat graphing on this software, so you'll have to bear with me. Best I can do. So now let's graph this one right here. Okay. So in this particular line, we know the y-intercept is negative 2. The slope is negative 1, so that's negative 1 over 1. So we're going to go down 1 over 1, down 1 over 1, and so on and so forth. And this continues up to the left as well. And if, using that whole slope method doesn't really work for your brain, then just plug in points for x and calculate points for y, okay? So it looks like these things intersect right here at negative 1, negative 1. It looks like right where the lines intersect. So that was our third step, to make an observation. Well, the fourth and final step is to, once you determine where they intersect, to double check it. So we want to now double check that negative 1, 1 as an x and a y will make both of these equations true. And I want to go back to the original equation, not what I rearranged, because what if I made a mistake in my rearrangement? This is a great way to check that. Okay, so let's plug it in. If my x value is negative 1, I can do that. And if my y value is negative 1, I have to plug that in here. I'll plug that into both equations. Now let's take a few notes here. On this portion right here, I had a negative 1, right? Because I had to plug in negative 1 for x, and the x was already negative. So this is going to be on the bottom, rewritten as negative 1 equals 1, positive 1, minus 2. So negative 1 equals negative 1. It worked. It's a true statement. Up here, same thing. Positive 4 on the left equals 3 plus 1, so 4 equals 4. So we got 2 true statements. That means that we were correct in our determination that negative 1 is indeed a solution for this system. Now, if they intersect somewhere in between, like let's say we had an intersection right here on the grid, you would have to do your best to estimate. And that is where the limitation of the graphing method comes in. Sometimes it's hard to tell where they exactly intersect. Okay, that was the longest example. Now I'm going to quickly show you 2 examples of infinite solutions and no solution. Okay, let's do that. So that last problem that you guys saw had one solution. It had one solution because, pretend we have a blue line here and now we have a white line. It had one solution because they intersected at one point. And I'll just ask you, 2 straight lines, if they're going to intersect, can they intersect more than once? Well, not if we're not in two-dimensional flat space, right? This line's never going to curve around and come back and run into this line. So if they're going to intersect, there's going to be one solution, right? So that was the kind of problem we just did, a one-solution problem. We're going to get an x and a y value. So now let's go over a concept of what would make something no solution. Well, let's think about it. No solution would indicate that the lines would never intersect. And I'm wondering if you've thought about that yet, if you've kind of figured that out. No solution, maybe parallel lines. Two lines that would never, ever intersect. And I think that makes a lot of sense. So if you graph two lines, and you notice that they have the exact same slope, but different y-intercepts, so they're parallel, there's going to be no solution in this case because they're never going to run into each other. There's never going to be that x and y point that works for both equations. Okay? Now let's talk about the last kind of possible solution, and that would be a no solution possibility, right? So it is possible to have, oh, I already did that, no solution. That's what I just talked about, parallel lines. The last possibility for solutions would be infinite solutions, right? So if the lines are parallel, there's no solution. But how can we get something that would present us with infinite solutions? Let's think about that. Well, perhaps if we thought about it in this way, if it's going to have infinite solutions, then that would mean that two lines intersect at every point. That seems odd. So that would mean they would definitely need to have the same slope. But what else would they need to have in common for that to occur? Well, if you look at this line here, like y equals 2x plus 1, and let's say you were given that line, and then you were given this line, okay, negative 2x minus 1 equals y, right? Well, these don't necessarily look the same right off the bat, or excuse me, negative y. These don't necessarily look the same right off the bat, right? This looks a little different than this one over here does. But if when you're rearranging these equations, when you're putting these equations into slope-intercept form, into a form that's easy for you to graph, you may notice that, hey, this one's already easy to graph, so you'll graph it, right? So you'll get a line. And when you rearrange this one, you'll probably do something like immediately switch the negative y and the negative 2x and minus 1 around, because we like to have the y on the left, and then make everything positive, right? Multiply everything by negative 1. So it becomes a positive 2x plus 1. And we don't need to show that positive sign. You might notice right away that when you rearrange them, hey, these things are exactly the same. These lines are the same. So to have infinite solutions, you're literally going to have two lines on a graph that are going to be exactly the same. They're just going to overlay each other for eternity, and so all points on those lines will be a solution. All right, I think I've been talking at you long enough. So we've reviewed the concept of a system. A system is of two or more equations. We talked about the solution types: one solution, infinite solutions, no solution. Be careful though, sorry I got interrupted by an announcement. Be careful with the one solution problems. Be careful with them because you should check them. You should check them by plugging in the solution that you think would work for both equations and make sure they're true. All right, guys, good luck with that assignment. The first 6 problems are just like the ones I gave you, and then the last problem takes a little bit more of a real-world approach, and so have fun with that one. Have a good one.